Okay, example 6-2 is about a free hydraulic jump that was formed in a horizontal rectangular channel with a bottom width of B0 equal to 2.5 meter. And the water depth at the upstream of the hydraulic jump is 0.12 meter. And the flow discharge is 3.5 cubic meter per second. So the question asks to calculate the length of the jump based on the proposed equations by different researchers. So the idea is that how we can calculate the length of the jump and how close or different are the proposed equations. So three proposed equations are tested here: Bradley and Peterka in 1957, Hager in 1992, and Schulz et al. In 2005. So if you go to the chapter 6 of the textbook, you can find those equations. So I have the equations for Bradley, Peterka, Hager, and Schulz. So as you see in all equations, the length of the jump is correlated with Y2 and fluid number at the upstream. So before we start using these equations, we need to calculate Y2 and fluid number in the upstream. For Schulz equation, we need to calculate Y star as well. So we know that the fluid equation for rectangular cross section is V1 divided by a square root of GY1. So I can also incorporate the continuity equation and write V1 as Q divided by area. So gives me the same thing. So I have V1 here. So this charge is 3.5 divided by 2.5 times Y1, which is 0.12, multiplied by a square root of 0.12 times 9.81. And that gives you the fluid number of 10.75, which is considered as a strong jump. So then we need to use Belanger equation, having the fluid number in section 1. Then we can use Belanger equation to calculate the conjugate depth. So Y2 over Y1 is equal to half minus 1 plus the square root of 8 through the square plus 1. So if you put the known values, you have one unknown, and then you will get Y2 equal to 1.77 meter. Then we can start with using the Bradley and Peterka 1957, which the length of the jump is lambda and the difference between the conjugate depth. So lambda is recommended as a value of 6.9. So Y2 minus Y1, and if you calculate them, you will get 11.385 meter, which we can roughly say that is around 11 meter. Because the value of lambda is the average value that recommended. So it's ranging between a wider range. So the next equation is proposed by Hager, and it's a non-dimensional length of the jump, LJ divided by Y1. And we use the fluid number as section 1. If you calculate, you will get LJ equal to 10.989, which is roughly 11 meters. So you will see that Peterka and Hager's equation pretty much gives you the same value. And then Schulz et al., it requires a little bit more calculation in terms of determining Y star, which is the ratio of Y1 divided by Y2 minus Y1, 0.073. And then you use the LJ, which is a function of Y star and Y1 square. And if you do the calculation, you will get LJ equal to 10.96, which is roughly 11 meters. So you'll see that over the years, equations becomes more complicated, but they will probably give you the same results.